Hả? Thằng nào? Thằng nào làm cái đây thôi? Thằng nào? Oh my god. Nhiệm vụ mày bảo vệ đấy. Các bạn khác có một cái. Oh. Summary. Okay. So for this is the summary. So of course you need to read for yourself at home. Okay. This is the summary of lecture 1. Okay. And we have homework. We have problem 1, 2, 3, 4, 5, 6. 6. We have 6 questions for homework 1. Okay, and we have 1 week to finish homework 1. Okay, yeah. Yes. Now we go to another lecture 2. Okay, for lecture 2 we have 2 parts. Lecture 2 part 1 and lecture 2 part 2. Okay? I also uploaded the PDF files of lecture 2 part 1 and part 2 into VTU Moodle platform. Okay, you can download it. And Mr. Hill, he is the lab engineer, who is the lab engineer of environmental technology, will guide you to do the lab sessions of this course. Now, we study synchronous generators, SG. Synchronous generators. Look, this is the diagram of exactly this is the construction of synchronous generators. We have stator, we have rotors, we have a fan, we have a rotor shaft. Okay, we have exciter here. Okay. And this is the cylinder pole construction. So when we finish lecture 2 part 1, you can get many knowledge. For example, you can understand the equivalent circuit of asynchronous generators, how to draw the phasor diagrams of synchronous generators. Okay. You need to understand how to calculate the power and the torque of the synchronous generators. Okay. We have the ability to derive the characteristics of a synchronous machine from different measurements. Okay, we have two common measurements. The first one is OCC. OCC means open circuit. Open circuit. Open circuit. OCC. Open circuit. Or we have OCC. Or we have short circuit. SCC. We understand how terminal voltage change with different load, kind of load. Okay. We also know how to calculate the terminal voltage as different load condition. Okay. And this one for lecture 2 part 1, and this one for lecture 2 part 2. Maybe tomorrow we discuss this one. Okay. Now session 2.1. We study on construction of synchronous generator. Okay, of course we know we have two main parts. The first one is stator, and the second one is rotor. Right? These are two main parts of any AC machine, typically for synchronous generators. Okay. We discussed about stator. Okay. So for the stator of synchronous generators, we have winding, right? We have winding. How many windings we have? 3. Right? Phase A winding, phase B winding, phase C winding. Okay, and we have what? We have magnetic core of the stator, right? Of the stator. Okay, to move the winding. Okay, rotor. So look. Stator winding. Okay. Sometimes we say stator winding, sometimes we say armature windings. Armature winding. Okay. For the rotors. For the rotors, we also have rotor winding. Rotor windings. Yeah, ABC, AS, BS, CS, and this is AR. VR, CR. That means phase A and the rotors, phase B, phase C. Okay. Winding. Or sometimes we say this is field winding. Why we say field winding is because the rotor winding will generate rotating. Rotating what? Rotating magnetic field. Okay. So rotating magnetic field, so sometimes we say rotor winding to be field winding. Okay? Yeah. Look here. Rotor winding or field winding. Rotor stator winding or armature windings. Yeah. How can you get the rotation magnetic field? So if we have the rotor, yes, here we have rotor winding, right? So for synchronous generators, we need to connect DC voltage, VDC, and you can get IDC. So if the rotor rotates with omega M, you can get rotated magnetic field. Okay? Sentence here, you know, a rotor's magnetic field is produced by either by designing the rotor A, the permanent magnet. Of course, we skip permanent magnet. We consider rotor winding. You know, we apply the DC current to the rotor winding. We can generate magnetic field. Okay. Yes. we have two kind of rotors. We have two kind of rotors. The first one is silent rotors, silent pole rotors, and non-silent pole rotors. Here, this is silent pole rotors. How many poles? 1, 2, 3, 4, 5, 6. We have 6 poles. Vietnamese meaning silent meaning cực lòi ra đây là ghép từ lòi ra đây này, lòi ra đây. Okay. Yeah. So we say silent because we can clearly see the shape of the poles. Okay, very good. You can count, right? You can count 1, 2, 3, 4, 5, 6. We say silent. Yeah. Normally, we have 4 poles or 104 poles for the silent. Now, non-silent. Look, a non-silent poles is a magnetic poles with winding embedded flux with the surface of the rotors. Okay, look at this one. This is the rotor winding, right? Okay, this is cross, this is not. That means come in, go out, go in, go out. Look, here, go in, out, in, out, blah, blah, blah. That is okay. So for silent pole rotors, the number of poles is 404. So for silent pole rotors, the number of poles is less than 4, normally 2. Normally 2. Okay. You know, for non-silent pole rotor, the length of the rotor, is longer. And if we go back to the silent pole rotors, the length of the rotor is smaller, but the diameter of the rotors is bigger. Because more poles. Yeah, so the diameter is bigger. Okay. So if we compare the speeds of the silent pole rotors and non-silent pole rotors, so the speeds of silent rotors is less than the speed of non-silent rotor. Okay. Of course, because the diameters of silent pole rotors is bigger, you cannot rotate so fast. You know? Look, why? Because this is the diameters of silent poles is bigger, so sometimes if we cannot get symmetrical, non-symmetrical, very dangerous, you know. So if we have some distortion here, that means the rotor is unbalanced. And if the rotors rotate so fast, we have more radial force, and then the bearing cannot withstand, and sometimes burn out. Okay, so that is the reason for silent poles. The speed is low. Otherwise, non-sealant. For non-sealant, you know, the diameter is smaller. So if these non-sealant rotors rotate very fast, we need more length to keep the balance. Okay? Yeah, you can compare. This is sealant holes. How many holes? 1, 2, 3, 4. This is non-sealant holes. We just get 2. That's 2 holes. You know. And this one is suitable for hydro power plant. Hydro power plant. And this one is suitable for thermal power plant. Okay, for thermal power plant, yeah, we need very high speed. Okay, so for hydro power plant, we need a dam, right? A dam, and here we have water, and then here, okay, follow the water pipe, and here we have the generator here. Okay, so the water flow from the rubber dam and come to these synchronous generators. The space is small. Okay, this is hydro power plant. Okay. And for hydro power plants, of course, we should use water turbine. Okay. And for thermal power plants, we use gas turbine. Yeah, you can see here, this is the magnetic core of the stator, magnetic core of the rotor. Okay. And remember that for synchronous generators, we need the DC power supply, right? DC power supply. Or we say here, we need the external DC source, okay, to the rotor to generate the magnetic field. So that's the reason here, you know, it is a rotor. So here we have two slip rings. Vietnamese name mini one the slip rings. We need a brushes, carbon brushes, and we only need DC power supply. So we have two brushes, positive and negative. Okay, to inject the current into the slip ring and then come to the rotor winding. After that, we have the rotor current. We have rotor current, so we can generate what? We can generate PR. Okay? Okay, PR. Magnetic distance from the rotor. Okay? So how can we get the external DC power supply? You know, yeah. Maybe we use battery. Okay, with your battery, you can supply the DC current into the rotor winding. But this way is not good, because sometimes the lifetime of the battery is reduced and the battery lost energy. Skip it. We don't use battery. Battery like the backup method, the backup solution. We think about this one. Look, okay. This one. So for this one, we don't need brushes. We don't need brushes. We don't need slip rings. Why? Because if the rotor rotates, that means slip rings rotate. And we have the current from here, so they will generate the acting. The acting. Right? Or we say sparking. Okay? And sometimes, you know, we get corrosion here. Yeah, that means the brushes will be damaged after some time for use. Okay, so we think about, we move slip ring, we move brushes, we use this configuration. Yeah. So this is stator of the synchronous generator. This is the rotor. This is stator. This is rotor. This is the fan. Okay, for cooling. For cooling. So this at the stator terminal, we can get AC voltage, right? Yes. And the AC voltage will come back to AVR. What does this mean, AVR? AVR means automated voltage regulation. Okay. Yeah. So we control the voltage. We adjust the AC voltage, and then back to another generator. This one we say is additional generator or supplement generator. Okay. Now we have exciter. That means field winding. Okay. So this generator, this small generator, and the rotors of synchronous generator have the same shaft. The same. So if the rotor rotates, that means this generator rotates, and we generate the AC voltage. After that, we rectify AC to DC to supply the DC current to the rotor. Okay? So this is a good way. We don't use slip rings. We don't use brushes. We just use additional generator here. And we have the same shaft with the rotors of synchronous generator. Okay? So if now we go to the hydropower plant, we cannot see slip rings and brushes because we don't have. They use additional generators. Okay? Any questions? Questions? Okay, so you should have maybe 3 minutes try to understand the configuration of synchronous generators here. Okay? After 3 minutes, I will give you some questions and you answer to me. Good. Okay, so here, you know, we have this is synchronous generators. We have main stators. This is main rotors. This is cooling fan, bearings, shafts. And I mentioned before, this is the additional generators, or we say permanent managed generator. Permanent managed generator. Okay? Yeah. So if the rotor rotates, that means this generator is working. Okay? Yeah. And this one is field winding. The stator is the rotor. And at the rotors, they will generate the AC voltage. And here, you know, this is normally this one is diode. It's a diode. We use diodes, 3 diodes, to rectify AC to DC. And then we supply the DC current to the main rotor. Okay? You understand? Yes. Okay. So the diode? Yes. Okay? So, now, but this one is physical model. It's a physical model. Okay, so we think about, we get the equivalent circuits for physical model, right? Okay, yeah. So now, look. This is the main rotor, this is the main generator. So here is the main generators. How many phase? 3 phase. For example, here is phase A, phase B, phase C. So this one is, I mean, the outer ring. The outer ring is main stator. And the inner ring is the main rotors. Okay, so we need the field winding. We need the field winding. So this is my mistake speed. This is my mistake, right? How many winding we have? 1. Field winding. Sorry, my mistake. Sorry. Okay, only 1 field winding. Sorry. Okay, so come back. And this is the additional generators, right? We have the same shaft. So here we have the same shaft. Okay. And you know, when this one generates AC voltage, look, AC voltage back. Okay, we can use single phase or 3 phase. In this case, we use single phase. That's enough. Okay, so the single phase come back here, and then we rectify AC become DC. Look, this is rectifier. We rectify AC become DC, and then because this is additional generator, so this is field winding. So the DC current will come to this winding, so we generate a magnetic field. So if the rotor rotates, this winding will induce the voltage. Okay? But the voltage is AC, right? AC. So we need to use rectifier again to rectify AC to DC and then supply to the main rotor. Okay? So now we have the rotating magnetic field in the rotor to the synchronous generator as well. Is it clear? Yes? So for this one, we cannot see any slip rings or process. Okay. This is the real picture, you know. This is the generator rotors. Okay. This is the additional generators. We have exciter rotors. You know, here we have rectifier. This is diode. Okay. So we rectify AC to DC and then supply the DC current into the main rotor. Of course, we have some explanation here, but you should read for yourself. Okay. Now, you have 3 minutes try to understand these circuits. Okay. Last year, I did one question about this diagram, and some students cannot explain. So we design how many